Right. We are going to focus on traffic engineering side of MPLS. We see MPLS makes the uh, forwarding of packet faster. We also saw along with MPLS and BGP together, we can have layer 3 VPN. Also layer 2 VPN if needed for dynamic discovery of BPLS peer members. Now we have come to something called traffic engineering with MPLS, which needs RSVP to signal, not LDP. That's the difference here. If you have a layer 3 tunnel already existing, that is LDP. You already have MPLS, MPBGP layer 3 VPN, that is LDP VPN. Along with that, some people will enable traffic engineering, then you need RSVP also. But now we are not focusing on L3 VPN, you see here. We are not focusing on L3 VPN. So LDP will not come into picture here because we don't need LDP. We need someone to signal by approving a path. LDP cannot do this. LDP can only distribute labels. Here, RSVP itself can do it, giving a path and distributing the label. So MPLS traffic engineering, do we need LDP? Answer is no. MPLS traffic engineering uses RSVP, which is called as Resource Reservation Protocol. So let me write down here. MPLS Te, traffic engineering technique. This is going to use resource reservation. So don't put double R. Resource reservation, S only you put. Reservation, V we put RSV reservation. So this you can call it as a reserve protocol, a resource reservation protocol, TE. Now, resource reservation protocol is going to set you path and provide the labels needed to use the path. I repeat. When you don't have MPLS traffic engineering, I repeat, when you don't have RSVP, you will be simply running MPLS only. MPLS is not a routing protocol. MPLS is going to give label and distribute label using LDP. Now, what determines the path? It is the routing protocol. Let's say so what happens is when you use OSPF, what will happen is only the upper path will be the selected path. ISIS cost. Now ISIS also is going to say upper path only. ISIS don't consider your bandwidth. That is why I have written in orange the link cost, the ISIS cost. Green one is for OSP. OSP will auto calculate the cost based on bandwidth. Let us say OSPF has said we'll take the upper path. ISIS also will say let us take an upper path. Let us take any one protocol. Let me use ISIS because you came up with the ISIS questions earlier. So let's say you have ISIS protocol. ISIS will not pick the below path. Cost is the reason. Cost is high. Cost is high. So A goes via B to C, and that is the only path A will take whenever it wants to go to C, even if there is too much of traffic to send. So, see, even if there is a huge amount of traffic to send via B, send to C from A, it will always go via only B because according to the routing protocol ISIS, that's the cheapest path. So you are not able to utilize effectively this path. You are not able to utilize the available bandwidth even when there is too much of congestion. You manage only to go via this path because that is the only path your routing protocol has put into your routing table. What is ECMP? Where is the equal cost? So what happens is, though you got a path at the bottom via D, that path is not at all considered even after experiencing huge congestion via B. At least, during the congestion, it should try to send some traffic via the below path. But you see, the routing protocols don't have that knowledge. Routing protocol or routers don't have that knowledge to do that. It will only see the routing table. Routers will only see the routing table. The route that is there in the routing table alone can be used for packet forwarding. The alternate path may be there in the database, ISIS database or OSPF database, but they are not designed to use the path which is not there in the routing table. They are not designed to use the path in the database. They can only use the path which is in the routing table. As a result, what happens? Even when there is a congestion, even though there is a huge amount of packet getting lost, this is not at all used. Path is there, but not ready to use. A is not ready to use it. Routing protocols, they don't have that knowledge. Routers don't have the knowledge to use the other path during the congestion. At least during the congestion it should use, but it is not capable of doing it. When we enable MPLS traffic engineering, you will be effectively utilizing the available bandwidth, which in turn reduces the congestion and definitely it is going to improve the performance of your network. You see the advantage of traffic engineering. When you notice a congestion here, some traffic will be placed in this path, though the path is not installed in the routing table. Even though the path is not there in the routing table, it says to go to C, you need to go to router B. There is no mention about D router to reach C. There is no mention about the path via D in the routing table. But traffic engineering can still use D when it finds congestion via B. So instead of going and making more congestion, to reduce congestion, you are effectively utilizing the available paths, available bandwidth. Definitely this improves the overall network performance. See what traffic engineering will do when a traffic comes in, the traffic says this traffic needs guaranteed 50 meg. It needs 50 meg. Now, there is no 50 meg in this path because it is already congested. Everyone is using that one path in the routing table. So there is no 50 meg. What RSVP will do, it will check whether that 50 meg is available between these two routers. It will go and ask, hello D, do you have 50 meg? It says yes. And then it says, hello C, A wants 50 meg. Do you have? And C says, yes, I am C. I am the final destination which A wants to come. I have 50 meg. This guy already said I have 50 meg to C. And C says, I also have 50 meg. You also have 50 meg. Why don't we advertise this path to A so that A can use this path? So who is doing this? C is doing this. C is telling you can come this path. That's called path message. This is called reserve message. This A to D and D to C is a reserve message. What is reserve message? It is checking whether there is a guaranteed 50 meg available. If it is there between A to C on this alternate path, the final router C will go and declare, initiate, generate the packet called path. For this new path, labels will be advertised. And this 50 meg will use that label to jump between the core routers and reach here. Once it reached this end, this path will be removed. And again, this path will be used if only there is no available bandwidth on the upper path. See, this path which is established between A to C via the below path is not a permanent one, not permanent. Only when there is no 50 meg available in the upper path. To avoid congestion, it tries this path. Otherwise, when it try going via B, that's going to cause congestion there. So, to setting up a new path when there is a congestion, you need someone to go to the alternate path and check the available resource. And if it is available, you want that someone to reserve the path, advertise the labels for this path. See, when you enable MPLS, you will not have label for this path. You will only have label for the path which routing table shows, isn't it? We saw MPLS assigned labels to only the routes that are there in the routing table. This route via D is not in the routing table. Will there be a label in the MPLS forwarding table? No. So RSVP only should reserve this path and advertise or signal the new labels for this path. Only for this traffic, these labels will be used. Rest of the traffics go via upper path using the label given by B. You see how dynamic is RSVP? Yes. Yeah. RSVP will advertise. MPLS will only generate the label. RSVP is the one which is going to distribute the label. RSVP TE is the one which is going to build this new path, and for this new path it will distribute the label. It's only RSVP, it's not LDP here. Because in database you have route. In database you have route, in ISS, not in the routing table because the cost is high. Routing table will always put the cheaper cost path, isn't it? Hmm. Hmm. No. It will be there in the layer 3 database. It won't be there in the forwarding information base. It won't be in the fib. It will be there only in the database, but RSVP will bring the path dynamically whenever needed into the fib, into the label fib, not normal fib, into the L fib. And once the path is finished once the traffic finished using that path via D, the path will be torn down. It will be teared down. It will be removed. Mhm. All paths. When there is a congestion in the primary path, it will send the reserve message via all other available paths in the database. And whichever responds first and whichever is the next low cost path will be utilized. The next low cost path. Okay. Now, so why do you need traffic engineering? In traditional routing, only the shortest path will be there in the routing table. As a result, uh, all will be using the same path and congestion will be there if the traffic is heavy. Whereas this traffic engineering with MPLS, it allows the explicit path selection. Explicit path selection. And what is explicit path selection? Even when there is no congestion, you can tell that if this particular traffic from this customer comes, use the below path. Let's say I have a customer who is a special customer for me, and I want to guarantee 50 meg always for him. Whenever that particular customer traffic comes, I will say take this path explicitly. I will tell to router A, if the traffic is coming from John and go, you should use this path. I explicitly define that path. So now when John comes, immediately it will go and check whether John's requirement is met in this explicit path, 50 meg. Yes. So path message will come, yes. And this is the label. Use label 50, use label 39. So now using that 39, it will come here. Using the PHP, it will come here. So what I'm trying to say is there are two ways in which the alternate path is taken. Number one, only when congestion happens, it dynamically finds the alternate path, which we discussed earlier. It dynamically comes and checks whether other paths are available, and if it is available with the enough bandwidth, it forwards. The second case, what we have seen is explicit path, whether congestion happens or not via B. Via B, everyone is using, even when there is no congestion. I don't care. If customer is John and Go, only check this path first. If that path has got 50 meg, use that path only. This also have got 80 meg available, but I don't want because it is John. For him, I have a dedicated path. Now you may have a question, what if some traffics are coming here and you don't have that 50 meg, only 20 meg available? Then what it will do, A will try this path, which is there in the routing table. If that has got 50 meg, it will use. When that also don't have 50 meg, only then it will come to E. Yeah. So traffic engineering allows you to have your own explicit path so that you can distribute the load manually. The second scenario which I said is I want to distribute the load. When John comes, always I prefer to send it via D because everyone going via B is not good. I want to distribute the load. So you can say MPLS traffic engineering allows you to have an explicit path selection so that you can do load balancing manually. You can distribute the load. Second one is avoiding congestion. You know that meaning of it. It also avoids congestion. Also, failures can be avoided dynamically. As I said, though this is the preferred path, when there is no enough bandwidth, automatically it goes to another path. There is no failure. There is no lag of service. When a path fails, dynamically it moves on to the next path. When the path don't have enough of bandwidth, dynamically it moves to the next path. So the second point is, first point is it distributes the traffic across multiple paths, which is a kind of load balancing. Second path we saw, congestion and failure is dynamically avoided. The third point is, it is providing the guaranteed 50 meg end to end. This is what? INSERV, no? Integrated service, I told you. It's not a good quality of service, but for John it is good. For other customer it is not good because it is going to go and block the below path 50 meg as long as John is using. When John stops using, then no reservation. It will give to others. As soon as John comes, it will go and grab 50 meg and reserve the path. So now what is important for MPLS traffic engineering to have? First thing is you need to have a link state routing protocol. A link state routing protocol only can provide link state database. What is link state database? The visibility to the whole topology. See, link state routing protocol advertises the link state information. within an area, all routers will have identical database. Whether it is OSPF or ISIS, within an area, they will all have identical database. So you have to put all this A, B, C, D in same area so that they will all have an identical database which RSVP can refer and see what all alternate paths available. Otherwise, how RSVP will know? See, if this path is getting congested, RSVP should query D only after knowing that there is a path to reach C via D. Otherwise, it won't query. It will query E only when A knows that there is a path via E to C. It won't simply query all the routers in the topology. It will first check the database and see whether there is a path available to C via D and E. If yes, then it will send the reserve message via both D and E, and then D will forward it to C if bandwidth is available between A and D, and C will send the path message. Likewise, E and C. Now, for A to know that there is also a path available via D and E, there is need for a link state database because routing table don't give those info. EIGRP, they don't maintain any LSDB. RIP never maintains. So the only two protocols that we have which maintains LSDB is OSPF and ISIS. OSPF and ISIS. So this is the only option, link state routing protocol. Traffic engineering, you need link state routing protocol so that RSVP will know the available paths. The other reason why OSPF or ISIS is needed is in order to copy the database of ISIS and ISIS or OSPF into RSVP so that RSVP can process and reserve the resource in this new path which is elected for the customer, John. RSVP is not a routing protocol to go and discover the topology. ISIS gives you the database. RSVP is going to copy the database and use it. Now, the other main reason why ISIS or OSPF is needed is they are extendable. ISIS or OSPF, they are extendable, meaning they have different packets or LSAs. Using that LSA, the new path information can be advertised, especially the opaque LSA, LSA type 9 and 10 and 11. Those are the LSAs which this RSVP is going to use to advertise this alternate path. To carry this info, that new label switch path, you need the extension header of OSPF or ISIS. ISIS have got LSP. ISIS has got, yes, correct, link state protocol data unit or packet data unit. It's actually protocol data unit. You call this packet also, LSP. So those LSPs are used to carry the new path information. Correct. Type length value, correct. Well, no, you have to enable RSVP on every single router. Every single router going to every port on the path on B and D, you have to go and enable RSVP. Don't focus on practical part because you're preparing for interview, but I am answering just your question. Yes, you have to enable RSVP on this port, 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 this port. It is interface level configuration. Yes. Yeah. No. Only if they support end-to-end QoS. Not many ISP support this RSVP traffic engine. No. Now, so the traffic engineering path, which is nothing but the path via router D, which is called as TELSP, traffic engineering label switched path, will use the SPF algorithm only, but normal SPF algorithm will show this path. This SPF algorithm says only if 50 meg is available, I'll consider. So we call it as constrained shortest path first, CSPF. So when you say RSVP, traffic engineering, you should not say SPF protocol, shortest path. We should say constrained shortest path first. Constraint is what? I want 50 meg in the path. If the constraint is met, then reserve the path. All right. So I spoke about path message, reserve message. Path message goes from head end to tail end. This is tail end. You're going from A to C. Head end, tail end. So you should know very well this thing. Path message is sent from head end router to tail end router. Reserve message is coming from where? Tail end message to head end router, tail end router to head end router if path is having that constraint met. You understand? Okay. No, RSVP means only traffic engineering. There is no other usage of this protocol. All right. Now, LSP, LDP. Correct. Next thing is, once the traffic passed to the other end from head end to tail end, once John finished using the path will be tear down. As I said, it will be broken. It will be no longer used. It won't be available. This new LSP path will no longer be available. For that, what it will send is, it will send a path tier message. Who will send? A will send path tier message, and final router C will send reserve tier message. They will tier the tunnel by sending the message, so that the bandwidth will be released for other users. That 50 meg via D will be released for other users. Next is, if there is any path in the after selecting after deciding to use this path, when you're about to push the path, if some error happens, immediately the router which is experiencing the error will push the path error message, and reserve error message will be sent immediately, so that the communication will be stopped right there and try to find another alternate path. So what I'm trying to say is, this RSVP has got all this messaging: path tier, reserve tier, path error, reserve error, and then the other one is path message, reserve message, all this thing. Path message will go from head end to tail end. Reserve message will come from tail end to head end if the constraint is met. Okay, so keeping all this in mind, you go through the document that I'm going to send you. It has also got configuration example. The whole story I finished. So there is nothing much to learn. There is something called fast reroute and all. It is not needed for practical. There's a theory. It's only for practical. And I have also put some traffic engineering questions. Right, fast rerouting is for quick conversions. Only that is the only thing you need to know. When failure happens for a quick convergence, you have fast reroute. It will take you to the alternate path. All right, I'll send you this document. Go through this. Okay. Uh, சொல்லுங்க.